All right, welcome back, grade 9 students. So this video is continuation for the previous two videos where we discussed lesson 1, lesson 2. Now it's time for lesson 3. By the way, we are still in chapter 1. And here we go. So the chapter or the lesson started with a question. So what is measurement? So a measurement is a comparison. Okay, we are always comparing when we are measuring. So let's take this boy as an example. He's measuring his weight. He don't know his weight. Okay, that's why he is comparing his weight to the balance. So it's a comparison between an unknown. What do you mean by unknown? Something that we still don't know. The boy still don't know his weight or his mass. Okay, that's why he is measuring his weight. Okay, so he is. It's a measurement is a comparison between an unknown quantity to what? To a standard. In this case, the standard is the balance that he is measuring his weight upon. Okay. Take another example. For example, measuring the height of a person. Okay. We don't know the. For example, I don't know my height. Okay. That's why I'm measuring my height in comparing to a standard. Let's say the scale. All right, so this is applied all the time to all kinds of measurement. All right, let's move on. This is another example of a painting found in France. It's a very old painting that scientists or a group of scientists, they estimate the age of this painting. So we have three groups of scientists. The first one claiming that the age of this painting is around 30,940 years plus or minus 610. The other group claiming that the age is 30,790 plus or minus 600 years. The third group is around 30,230 plus or minus 530 years. So what do you mean by this plus or minus? Plus or minus is the uncertainty. We are not sure. That's why we are uncertain. They are not sure exactly what is the age of this painting found in the cave. That's why we have to include the plus or minus. Means we are uncertain. We are not sure about the exact age of this painting. That's why we have to include plus or minus. If you notice, all three groups include this way of calculation, the uncertainty. Sometimes it's called as well the margin of error. Okay, in this book or in our lesson, they call it as uncertain or the uncertainty. All right, moving on to another example. Here is another experiment done by three students. They are measuring the height of a spring. Okay, so we have three students as well, similar to the previous slide where we have three groups. Here we have three students. The first one, when measuring the height of a spring, he said that the length of the spring is 14.6 plus or minus 0.2. Student 2 have another measurement. He's saying that the measurement of the spring is 14.8 plus or minus 0.3. And the third student claiming that the measurement of this spring is 14.0 plus or minus 0.1. So you see, plus or minus. Why? Because they are not certain about the value. Okay, they are still not certain, so that's why they include the plus and minus. So let's discuss it here in this picture. Here, let's make it bigger so you can have a better understanding of the measurement. Okay, here we have the three students, student 1, 2 and 3. So for the first one, he says that the measurement is 14.6, so this as average it's 14.6. This black line is 14.6, and those red one are the positive and the negative. So it's 14.6 plus 2 steps. Okay, plus 1, 2 steps. That's why it's plus or minus 0.2. So it's 14.6. One step is second step, so it's 0.2. The same is applied for the negative, so it's 14.6 minus 0. So the value of the spring, the length of the spring could be anywhere between 14.8, so this is 14.8 and 14.4. Okay, so that was for the first student. Moving on to the next student, he have a big margin of error. He has a big margin of uncertainty. So as average, he is saying that it's 14.8 as you see here. So this black line is 14.8 plus or minus this time 3 steps, 0.3. So it's 3 steps. So 1, 2, and 3 steps. Okay, so this maximum value, it's around 15.1. Or minus, again, it's 14.8 as average, minus the 3 steps, 1, 2, and 3 steps. So now it's around 14.5. So this is 14.5 as you see here. So that was for the second student. Third student has a different value. Okay, he's saying that the average length of the spring is 14, and as you see, the uncertainty is too narrow. He's more sure about his result because the uncertainty is very low. Okay, it's only 1 step, so it's 14. As you see here, it's 14, and on the graph it's 14. This value is also 14, plus or minus 1 step. So 14 plus 1 step, it's 14.1, and 14 minus 1 step, it's 13.9. So this value here is 13.9. So you see, we represent the values and the uncertainty with one graph, and that's how we do it. The plus and minus again represent the uncertainty, and it could be represented in such a graph. So what about the precision and accuracy of those 3 students? So let's see here and talk about the precision. So look at this again at student 1, student 2, and student 3. So we notice that there is something here regarding students 3. So he's saying that the average length of the spring is 14.0, but as I told you in the previous slide, he's giving uncertainty plus or minus 1 value. So it could be 14.1, so this value here, it's 14.1, or it could be 13.9. Okay, because it's 14.0 minus 1 value, it's 13.9. So you see, the margin of error here is very small. Okay, it's only around 0 plus or minus 0.1. So every time the margin of uncertainty, let's write it down, margin of uncertainty is small, like here. Okay, every time the margin of uncertainty is small, so we have a more precision, I mean. Okay, so we have a more precision measurement. Okay, every time, look at the other one, look at student 2 as well. Here we have the margin of uncertainty is big. As you see, it's plus or minus 3, plus or minus 0.3. Okay, the margin of uncertainty or margin of error is big. Okay, as you see, as explained, 1, 2, and 3 steps. All right, so here it's less precise though. So this student here has less precision. Okay, the same is applied for student 1, also is less precise. Okay, here student 3 is have more precision. Okay, we are not talking about accuracy, we didn't discuss accuracy yet, we are just talking about precision. So again, I repeat, student 3 have more precision because the level of uncertainty is so small. However, here for student 2, they are less precise because they have high uncertainty. All right, let's move on to the next slide. So, oh, too big. Okay, let's move on to this text. Here it's very important. Precision again, still discussing the precision of a measurement is 1/2 of the smallest division of an instrument. So I need you to keep this sentence in mind. It's a key sentence that we'll use it when we solve the questions. So again, how to define the precision of an instrument. For example, here we have an old instrument, here we have a new digital balance. So this is an old balance, and here it is a digital one. So from the first glimpse, which one you think is more precise? Of course, the digital one is more precise, because if you look, it's giving us more values. So if you count the zeros, it's around like 5 zeros, 5 significant figures. However, here the old one may be having 1 or 2 significant figure. Okay, so of course, the digital balance here is more precise. However, here is less precise. Okay, it's less precise. Why? Again, go back to the sentence. The precision of a measurement is 1/2 of the smallest division of the instrument. So the smallest division for the digital, having 5 significant figures, we look, of course, on the last digit. However, here having 2 significant figure, which is less precise compared to the digital one. All right, let's move on to the next slide. Now, accuracy is much easier. Accuracy is about giving the real value, the correct value. That's what I want you to think about accuracy. Accuracy has different meaning than precision. We can be very precise but not accurate, and we will see how. Okay, so accuracy having a real value, the correct value. I want to think about accuracy as correct. Okay, the correct value, the true value, the real value. Okay, that's what we mean by accuracy. Okay, let's look at this example here. We have this famous example. In the first one, we have 3 arrows, okay, on the target. All of them hit the middle of the target. All 3 of them hit the middle of the target. So all of them are accurate, okay, because they hit the real value, the true value. All of them are correct. They hit the middle, and they are precise. Look at them. All of them, all of the 3, all of them having the same value. They are precise. So both are accurate and precise. Okay, so precise and accurate, both of them are matched in this example. Let's look at the other one, at the second example here in the middle. We have the same thing. We have 3 arrows, okay, but this time they are not in the middle, they are away from the middle. Okay, they are away from the middle. They are still precise. Look at them, how narrow they are from each other. They are very precise, but unfortunately they are not accurate because they didn't hit the middle. Okay, they are not true. They don't have a correct answer. Okay, they are away from the middle, so they are not accurate. So look at this. They are precise. Yes, they are still precise, but not accurate. So they are precise. Here they are precise. Yes, it's precision, but they are not accurate because they are away from the target, away from the middle. Okay, let's take the last example here. Look at the 3 arrows. They are away from each other. Okay, they have big margin of uncertainty, like student 2 in the previous slide. Okay, and none of them hit the middle, so they are not accurate. Okay, none of them is true. None of them has correct answer. Okay, so they are not accurate in this case. We say they are inaccurate and imprecise. Both of them, okay, didn't match. It's opposite to the first example. So the first is opposite to the last. Here it's precise and accurate. Here it's precise but not accurate because it didn't hit the middle. Here they are not precise nor accurate. All right. Moving on. So, techniques of good measurement. We have a technique to have a good measurement. After doing the measurement, how to know if our way of measuring is true or it's good. Okay, so this is summarized in the last sentence. Look at this. The eye, when you look at this example here as well, 3 students or 3 eyes looking at the same value, some of them looking from above, from the middle, and from down. Okay, so which one you think will have the correct measurement or a good measurement at least? So with an eye have to be directly indirect in front of the measurement. Okay, so this one looking from above will have a wrong value reading the measurement, so this one will have a wrong measurement. Same is applied for the last one here. Okay, this will not also have a good measurement because looking from down, but this one here in the middle, because she is looking directly. Okay, we always have to look direct into the without having any angle. Okay, so only the middle one will have a correct reading of the measurement, and that's what we call as a good measurement. Okay, however the other 2 will have a bad measurement. Okay, will have different meaning or different values. All right, this is also that's what we call by parallax. Okay, look at this picture here, you have it in the book as well. So in this example, imagine us looking on this instrument. Here we are looking direct. Okay, here we don't have a parallax. Okay, because we are looking direct, and that's what we mean by it's a correct measurement. Okay, however, if you imagine here, I'm looking to the instrument from above, I'm looking at it from up, and here in this case I will have a bad measurement. Okay, so this one will have a good measurement, here will have a bad measurement because I'm looking from up to the instrument. However, here it will be the good measurement. All right, another example. Also, the example of precision and accuracy have to be applied to the GPS. Okay, GPS, that stands for the Global Positioning System, the GPS that locate people location. Okay, define people location here on the planet or on the map. Okay, so GPS to be consistent and precise and accurate with the measurement. Imagine having a GPS with wrong measurement, it will be a big problem. So it have to be accurate and precise. So to do that, the GPS system consists of 24 satellites. 24 satellites to give to be precise on one location. Okay, on the planet, orbiting the planet. Now let's move on to the questions. Let's start with the questions. So you find a micrometer, a tool used to measure the objects to the nearest 1000 millimeter that has been bent. Okay, so let's imagine we have a ruler it was bent. So how it would be compared to the high quality meter stick in terms of its precision and accuracy? Okay, so imagine we have a ruler. Okay, imagine we have a ruler here, but it's bent. Okay, it's not straight anymore. So if it's bent, you will not get an accurate result, will not get a real result. Okay, that's the main point. Okay, the measuring according to this instrument will not be accurate because it's already bent. Okay, it could be precise, yes, it could be precise because every time we are measuring a certain object we'll get the same result. Okay, but it's not accurate. This reminds us, if you remember, let's go back to the second picture in the arrows, if you remember, to the second one. This is also applied to the bent ruler. Okay, if the ruler is bent, okay, will not get an accurate result. It's not in the middle, but it's still precise because every time you are getting the same result every time and time, but we are not getting an accurate result. Okay, it's not real or it's not true anymore. Okay, let's go back to the questions. Okay, here we go. Okay, another example. Some wooden rules, also still talking about the rules, do not start with 0 at the edge. So if you can make this one bigger, this picture bigger, you can notice that the ruler, okay, the 0 is a little bit away from the edge. So why is that? Why we don't put the 0 here on the edge? Okay, because after using the ruler many times, maybe it will be worn out, okay, or worn off. We say that the ruler will be broken here on the edge, so it will not give us accurate result anymore. So that's why we put the 0, the designers of the ruler, they put the zeros a little bit away from the edge. Okay, so even if the rule will be broken here on this side or the other side on the edges, the 0 will not be affected. Okay, great. Let's move on. With this question, does parallax affect the precision of a measurement that you are making? What do you think? So again, the parallax affect the accuracy, not the precision. It's giving, if there is a parallax when we're reading an instrument, the parallax give us not accurate result. If there is, remember the picture when we are looking up or down into an instrument, the reading will not be accurate anymore. It could be precise, yes, but what's the point if it's not accurate? Okay, so the parallax affect the accuracy, so that it will not be accurate anymore. Okay, let's move on to the next question. Your friend tells you that his height is 182 centimeter. Okay, in your own words, explain the range of height. Range, okay, remember the range. Talking about the range, so you can tell it's a range of uncertainty. Okay, so my friend is claiming that his height is 182 centimeter. Explain the range of heights implied by this statement. So remember this sentence that I told you that will be used in the questions. The precision have to be looking on the last digits, the least digits, which is 2, which is the 10th of a centimeter or 1 of a centimeter, and it have to be divided by 2. So we have 1 centimeter that's divided by 2, which is equal to 0.5 centimeter. Okay, so this value have to be uncertain, okay, in terms of 0.5 centimeters. So if you want to put it in a range, so it could be like that. So it will be 182 centimeter plus or minus 0.5. Why 0.5 again? Because we look at the last digit, okay, which is 2 centimeter in this case. Okay, so it's about the unit, 1 unit of centimeter. So it's 1 unit of centimeter, okay, and it have to be divided by 2. So it's 0.5 centimeters. So the value have to be a range of uncertainty or range or of error. It have to be plus or minus 0.5 centimeter. All right. With the next question, here we have a box that have a length of 18.1 centimeter, a width of 19.2 centimeter, and a tall of 20.3 centimeters. So what is the volume of this box? If you remember the volume, we have to multiply the 3 dimensions all together. So the volume will be this value, it's 18.1, you can do it on the calculator, multiplied by 19.2 multiplied by 20.3. So let's do it together. It's 18.1 multiplied by 19.2 by 20.3. Okay, so the answer is, you will get it's 7054, and the unit is centimeter cube. But there is a twist here. remember in the previous section we discussed the significant figures. Here we have 3 significant figures, so the answer have to be or have to contain 3 significant figures. Okay, so we can round, or let's keep it this way, but we have to convert it to a 3 significant figure, and on the same time I have to write it on a scientific notation. Okay, so it will become 7.05, okay, by 10 power of 3 centimeter cube. Okay, so we moved the comma 3 times, 1, 2, 3, again 1, 2, 3 steps. Okay, we moved the comma 3 steps, that's why you put to the power of 3. Of course, centimeter cube doesn't matter, this is about the volume, the unit of the volume. Okay, keep this aside, we are just talking about the place of the comma, 1, 2 and 3 steps. So now the comma stands here, 7.05. I get rid of the 4. Why? Because I only need 3 significant figures as the question. All of the digits are 3 significant figures, 19.2, 20.3, 18.1. Okay, so that's the answer. Okay, it's 7.05 by 10 power of 3 centimeter cube. Okay, again, how precise is the measurement of the length? Okay, and for the volume. Okay, the length of this box is 18.1. Okay, it's about the last digits, so 1 is the last digit. So how precise? It's to the 10th of a centimeter, because here 1 represent 1 over 10 centimeter. Okay, so this one here represent what? It's representing 1 over 10 of a centimeter, so we call it 10th of a centimeter. Okay, so it's precise, it have a precision of 1 over 10 tenth of, or you can say it 1 over 10 centimeter or 10th of a centimeter. Okay, now question C, how tall is the stock of 12 of these boxes? So if one box has a 20.3, the tall of one box is 20.3. If we have 12, so we multiply by 12, so 12 or 20.3 multiplied by 12. So the answer is for question C, it's 243.6 centimeter. Okay, how tall? 12 boxes, they will be 243.6 tall. Okay, how does precise is the measurement of the height of one box? Again, the height of one box, which is also the same, 20.3. Also 3 is 10th of a centimeter. So, and for 12 boxes the same. Here 0.6, also it's about 1 over 10 of a centimeter. So we say that it's 10th of a centimeter. Okay, 10th of a centimeter, or you can say 1 over 10. Both will be correct. Okay, so this is for 12 boxes. It will be 10th of a centimeter. The same is also for one box. Also the same here, 20.3. So 3 is also about. So 3 is also about 1 over 10 of a centimeter. It's 10th of a centimeter. All right, let's move on to the last question. Okay, so last question, critical thinking. Your friend states in a report that the average time reported for a car to circle 1.5 mile track was about 65.440 seconds. So let's write this value down. So it's 65.414 seconds. So this was measured using 7 laps. So we use okay, the car is turning around this track by 7 laps using a clock with a precision of 0.1 second only. Okay, how many significant figure for this one? 0.1 second. Okay, so he's again, this was measured, so it's about measuring. Remember the first slide, we are comparing Okay, every time we are measuring means we are comparing to unknown to a standard. Here, after measuring using a clock with a precision of 0.1 second, so the clock has a precision of 0.1 seconds. How much confidence do you have in the result of the reports of this report again? So your friend is giving you this value. Do you agree with this value or no? And he's saying that he measured this time using a clock that which is at 0.1 seconds of accuracy. I mean for precision. Look at this. 0.1, it's only two significant figures. How in a balance, or let's say an instrument which have a two significant figure could measure a value which is 5 significant figures? That's impossible. That's impossible. A clock giving me only two values, only two significant figures. My friend, he's saying that using this clock, he got this value, which is 5 significant figures. I will not agree with the report or with the result of my friend. Because of that, I will say that his clock is giving two significant figures. He cannot give me a result or a report or an answer or a number which is 5 significant figures. If he gave me two significant figures as this one, 0.1, if he say, for example, 6.5 or 65, or I could agree with that, maybe. But in case he is giving 5 significant figures, I may not agree with this, with his result. That was for lesson 3. Thank you for your attention, and see you later in lesson 4.